So I already made a video for the warm-up problems for chapter 36. Now I want to go to the other extreme and do a video about the challenging problems, level 3 problems, among the suggested problems in this chapter. So these will be problems 30, 31 and 67. Okay, so there is 76 which is not graded, but that's not really a very challenging problem. I'll try to make a video about the rest at a later time. So we'll start with problem 30. So it says, in the Old West, a marshal riding on a train traveling at 35 meters per second sees a duel between two men standing on the earth 55 meters apart, parallel to the train. The marshal's instruments indicate that in his reference frame the two men fired simultaneously. In part A, which of the two men, the first one the train passes, A, or the second one, should be arrested for firing the first shot? That is, in the gunfighter's frame of reference, who fired first, and how much earlier did he fire, and who was struck first? Okay. So yeah, this is about simultaneity in some sense, but we can attack this problem with Lorentz transformation, and I had already promised that I would look at this actually. So we have a train track, there's a train and there's a marshal on this train. Right, so let's say they are moving in this direction, just we choose arbitrarily, at 35 meters per second. 35 meters per second, and they see two men, right, 55 meters apart, and in their reference frame, they fire their guns simultaneously. The question is, in the gunfighter's reference frame, which one has happened? So first of all, it's not very clear, it's not obvious what this 55 refers to, whether it is the, and they're then asking which one, by how much earlier they fired. So it's not clear which one this is, right? Is this the length as measured on Earth, in Earth's reference frame, or measured by the marshal? I can't really tell from the wording, so it's not clear whether this is L as measured by the marshal, or if this is L naught as measured by someone at rest with respect to Earth and with respect to gunfighter. So I'm going to just choose this. Okay, I'll just say L naught is actually 55. Okay, so they're saying which one was shot first, and you can make this argument with the light spheres and so on and so forth here, but you don't need to, right? If that kind of argument is confusing to you, then you don't need to make this argument. What you need to do here is to use Lorentz transformations, and this is what we are going to do here. And to do that, we need to choose some reference frame, and I'm going to choose the reference frame of Earth as our unprimed reference frame. Right, so S, this is Earth, or the gunfighter's reference frame, and the second reference frame, our primed reference frame, S prime is actually moving with this velocity 35 meters per second in the positive x direction. Okay, so I will also choose something. So this is the gunfighter A, and this is gunfighter B. The train first passes A and then B. So that's the one. That's the wording given in the book, in the problem. So that's not a choice. I have to do this. But I can choose their coordinates. So arbitrarily, I will choose my origin of this unprimed reference frame to be at the first gunfighter A, and then XL is going to be at this 55 meters. So XB is going to be at 55 meters. Okay. So it could be that it's something different. I chose this as L0. If it is L, it will be something different. I will need to add the correction there, but it's not going to change my argument too much. Now, in the reference frame, of the marshal, in the primed reference frame, the shots are fired simultaneously. So our events are gunfighter A firing and gunfighter B firing. So they took place at these positions of the gunfighters, of course. We also know that in the primed reference frame, these events were simultaneous. And we are required to find whether this is larger or smaller than, TA is larger or smaller than TB in the unprimed reference frame. Okay? Now to do this, we need to be able to write some expressions for TA and TB. And the easiest way to do that is, of course, to use Lorentz transformations, right? So I actually look this up from the book. So I can write the expression for TA. This is going to be gamma TA prime plus V XA prime divided by C square, and this is going to be TB is gamma TB prime plus V XB prime over C square. Right? So the transformation of one event has nothing to do with the transformation of the other. It just depends on the coordinates and time in the other reference frame. Right? Now, if you subtract these off side by side, TB minus TA is going to be gamma parentheses TB prime minus TA prime minus TA prime plus V by C square XB prime minus XA prime. Okay. Now TB prime is equal to TA prime, so that goes away. This thing goes away, and we end up with gamma V by C square XB prime minus XA prime. Okay. And in one reference frame, XB is to the right of well, XB is larger than XA, and from this it follows that XB prime must be larger than XA prime, because these are just this is just a coordinate transformation. It's not going to flip the previous direction of 2 points, and so this must be, because this is larger than this must be larger than 0, and if TB is larger than TA, A shot first, right? Now by how much? Well, by this number over there, by this thing over here. And how do we calculate that? Well, now this was, we know, so this is the difference between these 2 points, between two gun fighters in the prime reference frame with respect to the Marshall. So that's just the length contracted distance of the original 55 meters, provided that this is actually the 55 meters. It's possible that 55 meters is already this length, right? It's already the length contracted one, but I made this choice for 55 meters. So that TB minus TA, let me just erase this and put it here. So TB minus TA is gamma V by C square XB minus XA over gamma. All right, so these go away, and it's 55 meters V by C square. It's going to be something quite small. Okay? But this is how you would calculate. Again, this depends on what they mean by 55 meters. Actually, I think in the solution manual, they made the opposite choice. So the 55 meters was the distance between the gunfighters as seen by the Marshall. So this was already 55 meters. Okay. So if you make a different choice, you get a different number. But as long as you know what you're doing, your logic is first. Your logic is correct. It doesn't really matter. Right? But this is how you would do this. So the trick here is to really write down the correct reference frames, and then to write the expressions, and then you write your transformations. Here we were lucky that we were like just looking at some numbers that we can write down easily, but it is possible that you need to write further transformation laws and put the expressions in to solve these equations. So the equations that you get might be more complicated, but this is the logic. Setting up the reference frames, writing down the coordinates and the times for the events, and setting up the transformations. Okay? So I'm going to look at the next one, 31. Let me erase this. Okay. So we have two light bulbs, A and B, placed on the rest at rest on the x-axis at positions xa equals 0 and xb equals plus L. In this reference frame, the bulbs are turned on simultaneously. Use the Lorentz transformations to find an expression for the time interval between when the bulbs are turned on is measured by an observer moving at a velocity v in the positive x direction. According to this observer, which bulb is turned on first? Okay. So again, I'm going to set up the coordinate systems at the standard configuration. All right, so this is my primed coordinate system. This is my unprimed. Prime. I have two light bulbs. Right, so one is at the origin, xa equals 0, and the other one is xp equals L. Okay? And I'm told that TA is equal to TB. So the events I'm choosing are the turning on of these light bulbs. That's the obvious choice here. And the time for these two in this unprimed reference frame is the same. So this one is moving with some velocity v, and I am to compare TA prime and TB prime. Which one is bigger? Right, so for this you need the forward Lorentz transformation, so expressing the prime coordinates in terms of the unprimed coordinates. Now we have this expression. We have the expression that TA is equal to gamma TB plus Vx A by c square. Right? So you can either take this and try to invert it, or you can just notice that these Lorentz transformations must be symmetric. Right? So whatever transformation I'm seeing from going from this to that must be the opposite transformation going from this reference frame to the other. And the only difference between these two is that this is moving with respect to the primed reference frame is moving with respect to the unprimed one with positive velocity v. The primed one is going to move with respect to the unprimed one with negative v. Right? So that must be the only difference. So I can immediately, by making this deduction, I can immediately write down it must be the same transformation, except so this is not B, of course. This is A. Sorry. T. Man, I'm really sloppy. These are primed. Sorry about that. This is TA V xa by c squared, and this must be minus v, so I have a negative sign here. So you can either deduce this by looking at this, or you can look this up. Right? You can find this in textbooks. That is fine. And the same thing for b. So TB prime is going to be gamma TB minus V xb from c squared. So this change in sign from the forward and backward Lorentz transformations arises from the fact that these have velocities the opposite sign. Okay, so if I have this, now I can again take their difference and make a comparison, proceed in exactly, not exactly, but in a very similar manner. This is going to be gamma TB minus TA, the difference of the first terms, minus V by c squared xb minus xa. Okay. So TB is equal to TA, they're both 0, so this term goes away. And this one, we know, it's L squared, so this is gamma minus gamma L V by c squared. Okay. And all of these are positive numbers, right? And so this is a negative number, this is less than 0, which means that TA prime is larger than TB prime. Okay, so B was turned on first. Was turned on first in this reference frame. You can also make a comparison with the previous problem, I guess, and get the same answer. Okay, what else are they asking? Oh yeah, so they're asking for an expression. This is the expression. It is it's there. You need to plug numbers in, and according to this observer, light bulb B was turned on first. Okay, so third challenging problem, level 3 problem, was 67. Let's take a look at that one. There's this. So this is actually quite long. I will need to read this first. Let me erase the board and get some space. So we have a radar speed gun that emits microwaves of frequency of 36 gigahertz. When the gun is pointed at an object moving toward that speed v, the object senses the microwaves at Doppler shifts at frequency f. The moving object reflects these microwaves at the same frequency f. The stationary radar apparatus detects these reflected waves at Doppler shifts frequency f prime. The gun combines its emitted wave at f0 and its detected wave at f prime. These waves interfere, creating a beat pattern whose beat frequency is f prime minus f0. Show that v is approximately c times f beat divided by 2 f0. If f beat is much less than f0, and then they're asking for some numerical stuff. And then if the object's speed is different by delta v, show that difference in beat frequency, delta f beat is given by delta f beat is 2 f0 delta v by c. And then they're again asking for some numerical substitution. Okay, so here we have a microwave source, and we have an object that's moving towards this microwave source. And consequently, this object that's coming forward is going to see, so this is number 67. This object is going to see the frequencies of these microwaves at some shifted frequency. So they're coming close together. So I don't memorize the formula. I'm trying to show you how I remember which one is correct. I remember the form of the formula, and because the object is coming towards me, because the objects are approaching each other, the frequency is going to go up. Right? So this is going to be something like 1 over v by c divided by 1 minus v by c. Okay, square root. All right, and then this object that was coming is going to see microwaves of. So in their reference frame, of course, the microwave emitter, the radar gun, is coming towards them. They are at rest, so they're going to see things of this frequency, and they're going to emit or reflect waves at this frequency. But then now they became the source, and the source is moving towards the observer. The original radar gun also has the receiver, apparently, and they're going to see this shifted again. And so the f prime is going to be just f times the same factor. Right, so this is going to get shifted twice, and consequently, f0 f prime is going to be f0 times this factor twice, 1 plus v over c plus 1 minus v over c. Okay. And then they are going to subtract of these two frequencies. So this is the emitted frequency, this is the received frequency, and it's easy to make the interference between them and get the beat frequency. And this is related to the velocity. The velocity is given by the ratio of these two, beat frequency to original frequency, and then something. Right. So how do we find this? And they are saying that the beat frequency is much less than f0. Right. So the difference between these two is much less than this, meaning this is something like a 1 plus a small number, right? There is just a small shift taking place here. So knowing that, we can actually, I hope this reflection is not too bad, knowing that we can deduce that these must be small numbers, which is very realistic, of course. So we can write this as binomial expansion. So this is going to be f0 1 plus v over c times this. If I make the binomial expansion, its exponent is -1. It just moves towards. It becomes 1 plus v over c again, right? And I'm going to manipulate this further. I just multiplied that 2, so I get a factor of 2. I get the square, right? So f prime is going to be f0 1 plus v over c squared. And now again I make the binomial expansion. This is going to be f0 1 plus 2 v by c. Okay. And then from here, f0 by f prime is trivially 2 v by c. This is the f beat. Sorry, times f0. This way. Okay, and they're asking for V, so if you pull V out, V is going to be C times F beat by 2 F naught, which is the expression that we get, right? So this is of course approximate because we carried out binomial expansion. We assume that this number is small a number of times, right? While moving this to numerator, we assumed this is small, and then by taking the square, we neglected the v square by c square term. Again, we assume this is very small. Right? So this is correct. Now there is a linear relationship between the velocity and the beat frequency, right? So this means that as we change this slightly, this beat frequency is going to change linearly with that, right? So from this, it directly follows that delta V is going to be approximately C delta F beat by 2 F naught. Right? I mean, how would you do this? Well, you can just take some V1, some V2, and take their difference. This will correspond to some F beat 1 and some F beat 2. And you can, because the relationship is linear, just the difference in one side is going to turn into a difference the other side, right? By the same coefficients. So this is kind of trivial to follow, but maybe perhaps this this computation is not trivial. Certainly, seeing that this is going to get shifted twice, and so you get this factor twice, might not be trivial. Right? The reason why we are taking this factor twice is because it gets shifted. So initially, the object is the observer. So according to this observer, the source is moving with some velocity v with respect to them. So the frequency they feel is going to get shifted with respect to the source frequency by this factor. So they're going to see it at this frequency. Then the source, the observer becomes the source. Right now, the object is just reflecting it at what frequency? Well, the frequency they observed. Right? But now the original radar gun is the observer, and now the source is moving with respect to them with a velocity v. So again, it gets shifted by this factor. Right? So the final velocity observed at the radar gun is actually the original frequency times this factor twice. So we lose the square root, and then we carry out binomial expansion a few times, a couple times, and we get this expression. And the rest is just linear dependency. I would like to say a few more things about how, when this relationship is given, how you would obtain the relationship between the uncertainties. But yeah, for this problem, because it's linear, it's trivial, I'm not going to go into the detail.